Today's lecture will be on LeChatelier's principle. LeChatelier's principle is when an equilibrium is changed and how the equilibrium will shift material to either the reactant or the product side as a result of the stress to achieve a new equilibrium. There are three stress changers that we're going, or three ways to stress an equilibrium or change the concentrations of reactants and products in an equilibrium. You can first off change one of the reactant or product concentrations. You can change the temperature, and you can finally change the pressure. And the system will shift to counteract that stress. The first change that we're going to look at is a change in concentration. Let's go ahead and look at our example. We have the Haber-Bosch process. The nitrogen combined together with hydrogen gas in an equilibrium will form ammonia gas. For examples here, okay, if we increase the hydrogen in the flask, initially the hydrogen concentration is going to go up. What that means is now we have way more hydrogen gas in our container. So the likelihood that it's going to collide with a nitrogen molecule goes up. So the forward rate of reaction starts to go faster. The reverse rate of reaction is unaffected. So we ultimately end up seeing a shift right in material. So to reestablish a new equilibrium, we now have an increase in the concentration of NH3, and both the H2 and the N2 will decrease as a result of that to establish a new equilibrium. All right, our next example. We decrease NH3. If we decrease NH3, that means there is a smaller concentration of NH3 in our container. Initially, our NH3 concentration will go down. To establish a new equilibrium, because we have less NH3, the reverse rate of reaction becomes a fraction of what it once was. The forward rate of reaction is unaffected. Therefore, we see a net shift right. And to establish a new equilibrium, the NH3 concentration goes up, and both the H2 and the N2 concentrations go down. Pause the lecture here at this moment and try the last two on your own. All right, let's go ahead and go over the last two. If we decrease the N2 in the flask, initially the N2 concentration will decrease. That means the forward rate of reaction is now going to be a fraction of what it once was. There are less N2 molecules in our container, so the likelihood that N2 will collide with one of the H2 molecules goes way down. So the reverse rate of reaction, though, is unaffected, so we see a net shift left in material. So to reestablish a new equilibrium, both reactant concentrations will increase and the product concentration will decrease. The last example, if we increase the NH3 in the flask, now there initially we will have an increase in the NH3 concentration. Then to establish a new equilibrium, because there are more NH3 molecules, there's a greater likelihood that two of those are going to collide together, and the reverse rate of reaction increases. The forward rate of reaction stays the same. It is unaffected. Therefore, we see a net shift left in material. So you would end up with a decrease in the NH3 concentration to reestablish a new equilibrium, and both of your reactant concentrations would go up. All right, that is the first of three. The second one we're going to look at is changes in temperature. This is the first time we've really talked about energy in a chemical reaction. Endothermic reactions are reactions that take heat from their surroundings to the system. Endothermic reactions, when you touch a beaker containing an endothermic reaction, it's going to feel very cold to you. An exothermic reaction is one that gives off heat. So heat is transferred from the chemical reaction or the system to your surroundings. The first reaction that's shown there, you have energy on the reactant side. So therefore, the forward rate of reaction would be an endothermic reaction, and the reverse rate of reaction would obviously be exothermic. And you can see how changing the temperature shifts to the products and reactants. The second generic example you have listed right here, the forward rate of reaction is the exothermic reaction, and the reverse rate of reaction is endothermic. And you can see how an increase in temperature shifts to reactants or to products. So our example for this, again, we're using the Haber-Bosch process, N2 plus 3H2 in equilibrium with 2NH3. Notice now I've added energy. We have kilojoules per mole listed on the product side of our reaction. That means the forward rate of reaction is an exothermic reaction. If we increase the temperature, we're adding more energy into the system, that means the reverse rate of reaction is going to increase. The forward rate of reaction stays the same, and we ultimately see a net shift material left to the reactant side. So an increase in temperature would have those two concentrations going up and the concentration of NH3 going down. No surprise here, a decrease in temperature is going to give you the opposite effect. Let's take a look at what that would occur, how that would occur. If we decrease the temperature, that means we're removing energy from the system, so now the reverse rate of reaction becomes a fraction of what it once was. The forward rate of reaction is unchanged, so we see a net shift to the product side, and therefore the product concentration would increase, and both reactant concentrations would decrease. Moving on to our third method or third type of stress that equilibriums that can occur to equilibriums are pressure. An increase in pressure favors the side with the fewest number of molecules in the gas phase. You remember molecules are the right part of the mole map. We use Avogadro's number to convert from moles to molecules. For every 1 mole, there are 6.022 times 10 to the 23rd molecules. Because that is a constant ratio, we do not need to convert to molecules every single time. We can just simply compare moles on each side of the equation. So our first example here, again, the Haber-Bosch process, we've got a total of 4 moles of gas on the reactant side and only 2 moles of gas on the product side. So if the pressure is increased, we're going to favor the side with the fewest number of gas molecules. So we're going to see a shift to the right. If the pressure is decreased, then we will see, no surprise here, a shift to the left side or the reactant side. Okay? And this should make logical sense. As you're increasing the pressure, the molecules are going to strike the sides of your container, strike the other molecules more frequently, so the side with fewer number of molecules in the gas phase would be favored by increasing the overall pressure of the system. Now, volume. Volume changes. We remember in a gaseous system, Boyle's law stated that pressure and volume are inversely proportional. Therefore, if we have a volume increase, that means we're going to have a pressure decrease. And a pressure decrease would just simply have a shift to the left. Opposite occurs when the volume decreased, then the pressure is going to increase, and we would see a shift right. Last two scenarios here that we have on the board for LeChatelier's principle. The addition of a catalyst. Addition of a catalyst has no effect on the equilibrium. A catalyst is something that speeds up the rate of reaction without interacting with the reactants, becoming a reactant itself. So if we have our reactants in equilibrium with our products, we've established an equilibrium, which means we have a rate of X number of moles per second moving in this direction, and because it's in equilibrium, we have X number of moles per second moving in this direction. If we add a catalyst to the system, okay, that speeds up the rate of reaction, so now all of a sudden you have 2X moles per second moving that direction, but you also have 2x moles per second moving in the reverse direction. And don't get fixated on the specific numbers, 2x, 3x, 4x. Whatever the rate increase is, the rate increase will be the same for both the forward rate of reaction and the reverse rate of reaction. Therefore, there is no net change on the equilibrium. The last example we have, the addition of an inert gas. That also has no effect on the equilibrium. We remember from our gas law unit, we've got Dalton's law of partial pressures. So the pressure of the total system is going to equal the pressure of gas 1 plus the pressure of gas 2, pressure of gas 3, ... Now, if we were to go ahead and add an inert gas to that, we would now have a new total pressure, but pressure 1, pressure 2, pressure 3 all stay the same. All we've done is simply added another gas and therefore added the fourth pressure, P inert gas, or P4. So while P total increases, it increases because you've added a fourth gas there. P1, 2, and 3 ultimately stay the same. And that's why there is no ultimate effect on the equilibrium system.